This is lecture 8.1 on the nature of light. Okay, we're going to look at a couple of things in this lecture. We're going to look very briefly at spectroscopy, which is kind of the reason that light is important. And then we're going to look at properties of waves, including wavelength, frequency, and speed. And then we're going to look at regions of the electromagnetic spectrum. All right. Now, the reason that all of this is important is because of something called spectroscopy. And that's a very special way that we study the properties of matter. Okay. So if we have a sample, right, it could be, in some cases, it could be a solid, but typically it's going to be a solution. All right, let's say here's our sample. All right. And over here on the left, let's put a light source. I'm just going to draw kind of an old-fashioned incandescent light bulb. All right, so that's our light source. And light from the light source impinges on the sample, and some of that light comes out through the sample to the other side, and then over here there is a detector. And what we do in a spectroscopic experiment is we compare the light, the incident light, that's the light over here that's impinging on the sample, and we compare that to the light that comes out of the sample. And typically there's going to be some kind of change in the properties of the light. Very often it's a change in intensity of specific colors. And the way the light is affected by interacting with the sample tells us something about the sample itself. Especially what we can learn is we can learn about energy levels of the molecules in that sample. All right, so spectroscopy is a really important way for studying samples, and it works by comparing the different properties of light before and after interacting with a sample. So in order to use this as a technique, if we're going to compare the properties of light before and after, we have to really understand a lot about light itself. And so that's what this video is all about. Okay, so light travels in waves, and waves are a very common physical phenomenon. There are a lot of very different kinds of physical phenomena that all um, have wave properties. And even though they're very different, insofar as they're all waves, they have some similarities. So, of course, you've got waves at the beach, waves in water. There are sound waves, and radio waves are a couple of good examples. Radio waves, we'll see at the end of this video, are really just, they're actually very similar to light. They're just kind of a different kind of light in a sense. Anyway, so all of these things have very similar properties because they're all different examples of waves. All right, so the first thing with waves is speed. Waves have motion, they move through some kind of a medium, so they're going to be moving like that, and if they move, they're going to have a specific speed. Okay, different kinds of waves can move at different speeds, but for light, the speed of light is a constant, and that constant has the symbol c. So for light, the speed is given the symbol c, and that's always going to be 3 times 10 to the 8 meters per second. Okay? Just like all other constants. That value will be provided to you on exams or quizzes if you need it. If you think you need it, you don't see it, you can ask for it. Um, but the other thing I will tell you is as you're working study problems, you'll use that number often enough that when it comes to exam time, if you haven't inadvertently memorized that number, you probably haven't done enough problems. All right. The next thing is frequency. Frequency has the symbol nu, which looks kind of like a cursive V. Okay, it's a Greek letter. And the frequency is the number of waves that pass you in a specific interval of time. So, for example, there was a little guy standing here, and these waves are moving across from left to right. You can count the number of waves that pass every second or every minute or every hour or what have you. For light waves, we're going to be using uh, seconds because light waves are very tiny and they're moving very fast. All right. You can also think of this kind of like if you were over here, if you were stopped at this railroad crossing, trains going by, and you're sitting here, you could count the number of railroad cars that go by in a minute. And maybe they're rumbling by, and maybe you're getting 20 cars going by per minute or 20 per minute or something like that. Um, so the frequency is always going to be given in units of reciprocal time, right? So that's going to be 1 over time, right? The answer to any question about frequency is 1 over time. Like, for example, how often do you do your laundry? Might be twice per week, right? So it's 2 per week. You got time in the denominator. All right. So like I said, for waves, we're typically going to report this in reciprocal seconds. So that's 1 over seconds. Okay. If you take physics, you'll find that physicists like to use the symbol hertz, which is named after a physicist, and 1 hertz is 1 reciprocal second. Okay. I don't typically use hertz, but if you like using hertz and you want to, you're certainly welcome to. I will interpret that exactly the same as reciprocal seconds. All right. All right. The next one is amplitude, and that's basically the amount of energy carried in the wave. Um, and amplitude, depending on what you're talking about, can be defined as the height from the peak of the wave down to the midline, or sometimes it's defined as the distance from the peak down to the trough. Okay. Amplitude is not something that we're really going to be concerned with here. I'm just mentioning this because we're talking about properties of waves. That's one of the properties, but we won't actually use amplitude in our discussion. All right, and then the last one is wavelength. And wavelength is just the distance between two identical points on adjacent waves. Usually people would say the distance between two wave peaks, but it could also be the distance between two troughs or the distance at which it's crossing that midpoint. Those are all going to be the same. And that distance is the wavelength. And wavelength has the symbol lambda, the Greek symbol lambda. It's like the Greek letter L. And because this is a length, it's a distance, this is going to be in units of distance. The SI unit, of course, is meters. So we can write our wavelengths in meters. for the wavelengths of light that are most interesting to chemists, they're usually very, very tiny, and so we'll often report our distances in nanometers. Okay. But one way or another, it's always going to be a unit of length. All right. Now we've got these three different properties we're interested in: wavelength, frequency, and speed, and we want to be able to perform calculations among those three different variables. So we have to understand how those three things are related. There are at least two ways to remember this, and one of the ways that I remembered it, in fact, this is the way I remembered it for many, many, many years. When I was in college, one of my TAs told me that whenever you run into a friend and one of your friends sees you and says, "Hey, what's new?" you should just respond with C over lambda and then just walk on your way as if you hadn't said anything unusual or nerdy and just let them wonder what in the hell it is you're talking about. And so if you remember this, hey, what's new? C over lambda, then that will allow you to remember that C is C over lambda. And so that's one good way to remember this. And then if you have to solve for nu, then that gives you the equation right there. If you have to solve for either the speed or the wavelength, then you just have to do a little bit of algebra. So that's one way to remember it. If you like that, obviously feel free to use that. I always kind of enjoyed it. However, recently, as I've been thinking about this, I realized that's really kind of a silly way to remember this, particularly when there's something that makes a lot more scientific sense. And that is, if you just think about the variables themselves, right? The speed, C, is meters per second, or at least distance divided by time. Speed is always going to be distance divided by time. And the wavelength is going to be in meters, and the frequency is going to be in reciprocal time. So, therefore, the speed has got to be wavelength times the frequency, right? If you just look at the units, meters per second is equal to meters times reciprocal seconds, right? So if you just think about what they mean and what units they have, then this relationship is really going to be effectively is or should be pretty obvious. And if that's the case, that's a really sensible and reasonable way to remember that. All right, let's look at some calculations with this. All right, here's a simple calculation having to do with waves at the beach. Waves are approaching the beach at a speed of 3.5 miles per hour, and 15 waves reach the shore each minute. Okay, so and we want to know what is the distance between the waves. So let's set this up with our variables. Okay, first of all, if they're coming at a speed of 3.5 miles per hour, that's our C. Now C really, as a variable, C really stands for the speed of light. But I'm just going to use that for speed a little bit more generally here. So this is 3.5, and again, distance divided by time, miles per hour. Okay. The 15 waves reach the shore every minute, so that's our frequency. So the frequency is 15 per minute. And the distance between the waves, that's our wavelength, that we don't know. Okay. So now let's look at our algebraic relationship between these. We know that C is wavelengths times the frequency. We're trying to determine the wavelength, so we'll just divide both sides by nu. So lambda is c over nu. All right, so basically that's all we need to do. Although if you're paying attention, you might have noticed that we have a bit of a unit problem here. We've got our speed in miles per hour and our frequency in minutes. So we need to convert to get those to the same units. We've got to do that or else they're not going to cancel out probably. So we absolutely have to do that. I'm going to deal with this also though, because the question is asking us what's the distance between the waves. And if you've been to the beach, you know they're fairly close together, obviously. So reporting the distance between the waves in miles doesn't make a lot of sense. Feet would make more sense. So I'm going to do two things. I'm going to convert this speed. I'm going to convert the miles into feet and the hours into minutes. Okay, so we'll do both of those conversions before we do the math. Let's make some room here. All right. So our speed was 3.5 miles per hour. And we absolutely need to change the hours in order for things to work out. So that's 1 hour over 60 minutes. And it's going to make our answer make a lot more sense if we also convert miles into feet. And 1 mile, of course, is 5,280 feet. Let's check our units. Hours cancel. And miles cancel. That's good. And when I put that in my calculator, I got my screen's not working very well. All right, I got 308 feet per minute for the speed. Since we've only got 2 sig figs and our speed 3.5 miles per hour, we should keep this at 2 sig figs. I'm going to put a bar over that 0 to remind us that that number is really only 2 significant figures. All right. Okay, now we determined a little bit ago that to calculate the wavelength, or the distance between the waves, which is the wavelength, that this is going to be c speed over the frequency. So let's do that, and let's be really certain. It's always important. Be certain to include our units here. All right. So now we've got reciprocal minutes in the numerator and reciprocal minutes in the denominator. Those both cancel. So our units are going to be in feet. That's good because we're calculating the distance between the waves. When I ran that through my calculator, I got 20.533 feet. And this was 2 significant figures. So I'm going to round that to 21 feet. All right. Great. Okay. Let's look at another one. Okay. Here's one that's a little bit more like what we'll see in most chemistry tests. The yellow light emitted from a gas phase sodium atom has a wavelength of 589 nanometers. What is the frequency of this light? Because I got a little typo there. So sodium, actually, when you heat up sodium vapor, it emits a really bright light, and um, people started using this for streetlights back in the 70s and 80s. And in fact, back then, uh, before that, street lights were incandescent and they were kind of white. But after the 70s and 80s, they installed all of those, and so you notice a lot of street lights had kind of a yellowish color to them, kind of a yellowy orange color. Now you don't see that so much because they've come up with even more efficient LED lights, and so all those old yellow sodium lights are getting replaced by newer, whiter LED lights. Okay, so let's look at this calculation. Uh, let's again start by identifying our variables. That's always a good place to start. Um, so C, since this is light, this is a constant. C is going to be 3.0 times 10 to the 8 meters per second. The frequency, we don't know. That's what we're trying to figure out. The wavelength is 589 nanometers. Okay. Now let's look at our algebra. We can start with C, the speed of light is equal to the wavelength times the frequency. Okay. And since we're trying to solve for frequency, we can just divide both sides by lambda. So C over lambda equals nu. I don't know why my nu disappeared. Okay. And if you'll see, that's the same mnemonic I mentioned before. What's new? C over lambda. So this is exactly what we would expect. So to calculate our frequency, we just take the speed of light and divide by the wavelength. Okay. All right. Just as before, however, you can see again we have a unit problem. Our speed of light is in meters and our wavelength is in nanometers. So before we can do anything else, we need to fix that. Okay, so let's do a little unit conversion and then we'll plug it in and calculate our answer. All right. All right. So remember that there are 10 to the 9 nanometers in a meter. So take 589 nanometers. We want to convert this into meters. So we'll put our nanometers at the bottom. 10 to the 9 nanometers, 1 meter. And that gives us 5.89 times 10 to the minus 7 meters. Okay. All right, so to calculate our frequency, remember we just figured out frequency is going to be C divided by lambda. So this is going to be 3.0 times 10 to the 8th meters per second. And again, we always want to make sure we include our units. It's really easy to screw this up and make an algebra mistake right there. Anybody is prone to doing that, and there's nothing wrong with it. But if you put your units in, then you can catch those mistakes. If you don't put your units in, those mistakes are going to go right on through till your answer, and your answer is just going to be flat out wrong. All right. So when I put that in my calculator, I got 5.0934 4 times 10 to the 14 reciprocal seconds, right? We got seconds in the denominator there. All right. Since we've got 3 sig figs in our data, we'll round that to 5.09. So you could write this as 5.09 times 10 to the 14 per second, or if you wanted, 5.09 times 10 to the 14 hertz. Either of those would be fine. I'm going to stick with seconds. All right, great. All right, let's go on to the next one. All right, so we've been talking about light as a wave. Okay, the question is, if it's a wave, what is it a wave of? You know, when you go to the beach, you see waves. Obviously, the waves are made of water. When you talk about sound waves, obviously those are pulses in air, right? But what we're talking about here with light is an electrical field. If you have two charges, a positive charge and a negative charge, for example, that's going to make a field between them. And if you have a magnet, for example, a north pole and a south pole, then that's going to make a magnetic field like that, right? So I'll let you learn more about the ins and outs of fields when you take physics, but basically that's what we're talking about. And a light is just an electrical field. Well, we'll start with that. An electrical field that's oscillating so that the field strength varies up and down. And what's kind of interesting about it is that perpendicular to that oscillating, let's go ahead and I'll put an E here. Perpendicular to that oscillating electrical field is a magnetic field rotated at 90 degrees to the electrical field. And they are both simultaneously oscillating as they move through space. All right. And because that oscillation is an oscillation of an electric field and a magnetic field, we call this electromagnetic oscillation. And if you look at all the different frequencies of this, we call that the electromagnetic spectrum. Okay? I found this kind of fascinating when I first encountered this when I was in Gen Chem. I was really surprised to find, and maybe you will be too, that all of these different phenomena here, gamma rays, X-rays, ultraviolet, visible light, infrared, microwaves, it's not labeled here, microwaves and radio waves, those are all things that, well, many of them at least, gamma rays, X-rays, and radio waves are things that you probably think of as being very different, but they're all basically the same phenomena, and they're all basically the same as visible light. Visible light is just an oscillation in this very, 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 very narrow range of frequencies. So down here at the very short frequency, or let me say very short wavelength and a high frequency at this end are gamma rays. Right here. Okay. At the very short end of this are gamma rays. A little bit longer than that are X-rays. Okay. Yeah, I'll go ahead and put UV in here. We'll come back to UV. And then we've got ultraviolet, and then visible light. Visible meaning visible to humans, right? Some things, bees and such, can actually see UV. And then we've got the infrared, and then again, right right here, the label is missing on this graph, but that is microwaves. So the thing that you use to heat up your cheeseburger in the microwave is really the same as visible light. It just has a longer wavelength. And then radio waves. Okay, all right. Now, for all of these, and let me say down at the end here, this is long wavelength, okay? So that's the order going from shortest wavelength to longest wavelength. I would like you to know this order. I'm not interested in you learning all of these numbers across here, except for these numbers here. I do want you to know these numbers. I'm not interested in you knowing all of these numbers, but I would like you to know those in order, because we'll see later that the energy of these different kinds of lights is related to the wavelength. So this list here, which puts them in order of shortest wavelength to longest wavelength, is also the list in order from highest energy to lowest energy. And understanding the energy of the different kinds of light is important. So I would like you to know this list in order. All right, now let's look at visible light here also. Kind of wish I'd given myself a blank page here with more room left to write. Well, I guess we can just look at the picture. All right, so all of visible light is in this very tiny range right here, going from 400 nanometers to about 750, maybe 800 nanometers. We define the ends of visible light is what human beings are able to see, and what kind of light different people are able to see varies a little bit from one person to the next. But the generally expected range is about 400 nanometers to about 800 nanometers. And if you look at the colors here, this is important. The colors go in the order of the rainbow, right? So on the short energy, and you've got, I would call it purple, but most people would say violet. So at the short end, short wavelength, which I mentioned a bit ago, short wavelength is also higher energy. All right, so that's violet. And then it just goes in order of the colors of the rainbow: violet, blue, green, yellow, orange, red. And this is at about 400 nanometers. This is at about maybe 750 nanometers. Okay. All right. And then let's look at the ones on either side of that. Just before the violet end, the stuff that's just on the edge of that is ultraviolet. violet, and that name just means beyond the violet. So that's a way that you can always remember that UV radiation is right here. It's right up next to the visible light, and it's right on the violet end of the spectrum, just beyond the violet. And similarly, at the long wavelength end of the visible, right past that is infrared, or IR. And of course, ultraviolet people usually write as UV. So UV and IR. Infrared means just below the red. Infra means below, right? And so that means energy-wise, this is just this part right here. Energy-wise is just a little bit lower than the red end of the visible spectrum. All right. So you should know ultraviolet is just at the short wavelength or high energy end, just beyond the visible. On the other side of the visible is infrared, which is longer wavelength and lower energy. And in between from 400 nanometers to about 750 nanometers, it goes from purple to red and just goes in the color, the order of the rainbow. All right. All right. So we talked about light, and we said that it is an oscillation of electric and magnetic fields, and that it moves at 3 times 10 to the 8 meters per second. We looked at the electromagnetic spectrum, and you should know visible light goes from about 400 to 750 nanometers. 400 is the purple or the violet end, 750 is the red end, and of course, on either side of that is ultraviolet and infrared. And might actually, I meant to cut this part out. I have a whole thing on diffraction and interference, and I cut it out of this because the video is just a little bit too long. But you can read that part in your textbook. And the relationship between frequency, speed, and wavelength is given by this. It's a little bit tiny here, but C is equal to lambda times nu, or speed is wavelength times frequency. You should know that, and given any two of those, you should be able to calculate the third one. All right, great. All right, thank you, everybody. I look forward to seeing you all in the next video.